Alright, so what we're seeing right now is some time plots of sales for several products in some merchandise stores. As we can see, it's a daily data set, so a daily sales that spans from 2015 to 2019. And given the history of 4 years, we are asked to forecast the sales for the next year, so for the next 365 days. This project is going to be another project of long-term forecasting. Hey everyone, welcome back to my channel. We have studied NBEATS and we also have studied NHITS. Now we're going to study NBEATSx. Alright, let's study together. Alright, so far I talked about NHITS first and then NBEATS. And this is going to be the video that's talking about NBEATSx. But actually, the order of which model is developed first is not like that. So here's the timeline. NBEATS was the first model. And then they improved NBEATS to allow exogenous variables. So X in NBEATSx is for exogenous. Okay. So that's the extension of NBEATSx from NBEATS. But NBEATSx cannot choose the sampling rate like NHITS. So what we're going to study right now is in between NBEATS and NHITS. Okay, we're going to start with studying the framework first and discuss the differences and similarities between those models. And then we're going to talk about the dataset we're going to use and why I decided not to use the dataset that I used in the NBEATS and NHITS videos. And then lastly, we'll put our knowledge into practice to forecast the sales of these products. Alright, so NBEATSx, what we see on the left side is the full model. Okay, so this one is the full model. On the outside, it looks exactly the same as in NBEATS and NHITS. So the pink boxes are the blocks and they are grouped in stacks colored in purple. Okay. If we enlarge each block, we will get the diagram on the right side. What's inside the block of NBEATS and NBEATSx model is exactly the same. Okay, but for NHITS, there are some modifications. So the similarity that we can find in all three models is this part. So from MLP stack, and then the output goes to FC linear, so fully connected layers with linear activation function, and the output of those layers would be the coefficients for forecast and backcast. In NHITS though, before the block input goes to an MLP stack, the input is filtered by a certain sampling rate. And then instead of using basis expansion layer, they use time interpolation. We have two such parts. One is for generating the forecast and the other for backcast. So that's the only difference between NBEATS, NBEATSx, and NHITS. Oh, by the way, NBEATSx, unlike NBEATS, this model receives exogenous variable in addition to the main time series. Then what about NHITS? Can NHITS accept exogenous variables? Well, it's not clearly stated in the paper actually, but it's possible in the coding. I made this video of using NHITS for predicting gold price using some exogenous variables. You can check that out. Okay, and then another similarity among these three models is the use of doubly residual stacking principle. So this principle is basically taking the difference between the block input and the backcast and then use that difference as the next block's input. Okay, so technically speaking, the only block that receives Y and X is the first block in the first stack, so the top pink boxes on the left side here. I mean on the left diagram. Okay, and then for the rest of the blocks, they will just receive the difference between the block's input, the previous block's input, the previous block's input and the backcast. Alright, so let's take a look at this block. This is what happens in the block for NBEATSx. The block input is once again Y and X. Okay. The block input will go through an MLP stack, a multi-layer perceptron stack, and then the output would be H, the lowercase h. The size of h or the lowercase h would depend on the total hidden neurons in the MLP stack. In the coding section later, we will see that the default value is 512. So the size of h would be 512. Okay, and then this output would go to two different places. They're exactly the same actually, fully connected layers with linear activation function, but their task is different. One is for learning the coefficient for forecast, denoted by theta 4, and the other is to learn the coefficient for the backcast, so theta back. And then these data are used in the basis expansion layer. Okay, so the BE in NBEATS and NBEATSx is for basis expansion, and it's applied here at the end of each block. Now I want to talk about the block's inputs first, especially about the exogenous variables. Okay, so we have two types of exogenous variables, the static and the time variant one. In this particular project, we will use the time variant exogenous variables, that is the holiday events. Okay, so that's for the exogenous variables. Now we can move on to another big discussion, which is the basis function. The basis function we use determines the size and the dimension of matrix V and array theta. And it also determines the name of the block and consequently the name of the stack. Let's look at our diagram on the left side again. So in this diagram, this is just for an illustration actually, but let's say that we have two blocks in each stack. The activation function used in blocks within a stack have to be the same. And so if we say that the basis function for this particular block is a trend basis function, then the whole stack, we can say that the whole stack is called the trend stack. Okay, before we talk more about that, about basis functions, I want us to really understand about the main task at hand. Okay, so we want to forecast the daily sales for the next year. Our forecast won't be just a value, but an array of values. Let's say that we have this yellow array as our forecast. And actually, y-hat backcast can also be illustrated by this yellow array. And then if we want to have a mathematical equation to get the forecast and backcast, we can just translate the diagram to these equations. Okay, so they're actually just matrix multiplications. The multiplications of V, matrix V, and array theta. Let me draw it here. So y hat illustrated by this yellow array, and then equals V times theta. And then just like in matrix multiplication, if we multiply element-wise, the first row of V and all the elements in theta, we will get the first element of y hat here. In other words, to get the forecast or the backcast at each time point in the array, we need some features that are expressed in the columns of matrix V, and then we need some weights, like some coefficients, and that is learned by the linear by this part here, by the linear layers. Okay, now what is the total column of matrices V, and what is the length of theta? Well, you know what? I'll start from y-hat forecast. Sorry. So the forecast would be an array, right? The length is called the horizon, and it's denoted as capital H, okay, the uppercase H. And and then for the backcast, it's also an array, but the length is L. In the NHITS paper, it's clearly stated that L should be at least twice as long as the horizon, but I saw in the NBEATSx paper, it's not always the case. So for this particular project, I will set the L to be equal to H. Okay, let's move on. Let's talk about this. The lowercase h, as I said earlier, it's going to be... It's actually a matrix, come to think of it, right? Because this is a neural network, and these two are also a neural network. So the lowercase h would be a matrix, and the dimensions would be related to these two layers. Alright, now let's go back to our matrices V. So the V matrix for forecast, it has H rows, the horizon rows, and NS columns. And then for the matrix V for backcast, the total rows would be L. So it's consistent with the length of y-hat back. And the total columns is also NS. NS is the total features that I talked a few minutes ago. The total features that we need to use to determine the value at each time point in the forecast or backcast array. So y equals v times theta. Well, so looking at this equation, you might have guessed the length of theta. The theta forecast and theta backcast have the same length, and the length is ns. Or if you want to describe it as a matrix, then it has ns rows and one column. Again, ns would be different depending on the basis function we are using. Okay, oh, one more thing, x here, the x to denote the exogenous variables. It's a matrix with L rows and nx columns. Nx denotes the total exogenous variable. Okay, now we are ready to talk about the basis functions. The basis functions are divided into two big groups. The first one is the interpretable configuration, and the second one is generic configuration. So depending on how we want to set up our NBEATSx model, we have different basis functions. Okay. By using the interpretable configuration, we are trying to mimic the traditional time series decomposition. So the basis functions available here are trend and then seasonality. These two are available in NBEATS, by the way. And in addition to these two, we have exogenous basis. Okay, now let's discuss one by one. First up, the trend. So we can think of this trend basis function as a polynomial linear regression. Okay, so first of all, let's write this. So y hat, I will assume the y hat is for forecast, by the way, even though I don't write the for superscript. Okay, so y hat forecast is v times theta. And then, well, V is the basis matrix. So if we use the trend basis, we can rename the V to T, capital T. Okay, times theta. So these two lines are the matrix, it's the equation in the matrix notation. In the summation notation, we would have this line. Okay, let's draw the T matrix. So this is the T matrix, and this is the array, the theta array. And then the total columns for matrix T can be identified by using the upper bound and lower bound of the summation. So since the summation starts from 0 to n polynomial, that means the ns equals to the total polynomial degree plus 1. Okay, so when I equals 0, it's just the intercept. And then the lowercase t here, notice that it's printed in bold, indicating that this lowercase t is actually a vector. So it's an array, and it will start from 0 over h, the horizon, and then 1 over the horizon, 2 over the horizon, until h minus 1 over the horizon. Since we're talking about the forecast, okay. If we talk about the backcast, then it's going to be 0 over L, and so on. The denominators would be L, and the length would be L actually, okay. This vector t would put as a column, and each column has a polynomial degree. So the first column would get the degree 0. So this would be t to the power of 0. In other words, just a column of 1s here. And then on the second column, it will be t, just t, because it's t to the power of 1. And then in the third column, so this is t. And then for the third column, it's t squared. So the vector t, and each element in that vector got squared, and so on, until the total or the maximum polynomial degree. Okay, so let's move on to the next basis. It's the seasonality. We have this equation, so we can actually think of this basis expansion as fitting a discrete Fourier transform series. However, the theta is going to be arranged a little bit. So usually in Fourier transform, we would have cosine, sine, cosine, sine, because we have the cosine of this function of this value and then followed by a sine function. So it's always going back and forth, like cosine, sine, cosine, sine. But the theta, if you look at the index I here, we will have the theta array that goes like this. So we divide the theta array into half, and the first half is the theta for cosine functions, and the second half for sine function. And so what about the matrix V? The matrix V here, since we're talking about seasonality basis, then we can rename the matrix V as matrix S. And then if we divide this matrix into half vertically, on the left part, we have the cosines variables, and then for the other part, the sine variables. And then to compute the total columns in the matrix S, now it's a bit different. So we have to look at the upper bound and lower bound of the summation and these terms. Okay. Now notice that when I equals 0, this would be 1 because it will be the cosine of 0, which is 1. And this part on the second term, the sine of 0 would be 0. And so we won't use any coefficient stored for this particular index. It's not like we are not using, but we will double it. Okay, I'll write it here. It's going to be quite long. So for example, if we have the horizon equals 12, then the upper bound here would be the floor of 12 divided by 2 minus 1, which is 5. And then the expansion of the summation would look like this. And then look at the second term, sinus of 0 times the fifth theta. But we have the same theta 5 in the last row. So cosine of 2 pi times 5t over the n-harmonic. And HR denotes the n-harmonic, the total harmonic. Okay. Look at the theta. Those are the same, right? So it's not like we are not using the theta of this particular index, but it's just we already have one later as we increase the I. But still, since this part would be 0, then the theta here is not going to be used. So we have the horizon minus 1 as our total features. So in other words, to get the forecasted value at each time point, we need h minus 1 features. And the first feature is actually the mean. So the first value in the theta can be thought as the mean. Okay, and then the last basis function in this configuration is the exogenous. Again, let's say that y hat equals v times theta, and then if the basis function is exogenous, then we can rename it to x, and the theta denotes the coefficients. So this is matrix X, and this is array, the theta array. The total columns of this matrix can be determined again by the boundaries of the summation. So it's quite clear here that NS, if we are using the exogenous basis, equals NX, or the total exogenous variables. Alright, so perhaps this is an important thing to note, that we used doubly residual stacking earlier, right? So as we go further down the model, the input or like the time series would be, like filtered and filtered out. Okay, let's say that we are using the interpretable configuration, and the common setup would be putting the trend basis at the top, so the trend stack at the top, and then followed by seasonality and then exogenous. Both the seasonality and exogenous stacks won't get the raw time series, but still we ask them to detect the seasonality and the effect of exogenous variables to their respective inputs. Yeah, with that being said, let's move on to the generic configuration. So with generic configuration, it's actually a learned decomposition. So we don't decompose it in the traditional way, like trend and then seasonality, but this model can choose their own sampling rate, if you will. And so let's look at this. Y hat equals v times theta. And if we use the generic configuration, the matrix V can be renamed to an identity matrix. An identity matrix with dimensions h rows and h columns. Again, we're talking about forecast. If we're talking about the backcast, then we will use I, the matrix identity, the identity matrix with L columns and L rows. Okay, and then times the theta. We do know what an identity matrix is. It's very easy, right? So what is this telling us? Basically, it's telling us that whatever we learned in the linear activation layers, we use all the coefficients learned to generate the forecast. Now let's move on to the last basis function, which is the exogenous. So the exogenous basis is a little bit different depending on which configuration we are using. In the generic configuration, the basis matrix is called C, and it's denoting the context vector. This matrix is learned using a convolutional substructure. So it's involving sort of like encoder-decoder. Yeah, so it depends on the convolutional process we are using. I'm not going to go into detail over that, but yeah, it's basically learned automatically. The general theme in a generic configuration is like that. the model learns by itself instead of trying to mimic the traditional decomposition. And the dimension of this matrix would be H rows and NC columns. So the NC, NS, we talked about NS several times now, right? NS would equal NC. Okay, so here we are now in our Kaggle notebook. We have seen the overview of how NBEATSx works, and so now we want to apply this to the dataset that we've seen in the introduction earlier. First of all, I want to explain why I use a different dataset. So if you've seen those videos, I used an electricity production dataset. So the idea was we want to forecast the electricity production from renewable resources. But that dataset has only the consumption and production of electricity and the breakdown of electricity production based on the resources. If I want to apply NBEATSx to an electricity production dataset, then I need an independent feature that could explain or be an appropriate feature to the electricity production. And I don't have that. So that's why I decided to change to another dataset. So the dataset that we're going to use is actually a competition dataset that is from Tabular Playground series, January 2022. And the exogenous dataset that we're going to use is the holidays event. And so you can find these datasets in Kaggle. I think if you don't have a Kaggle account and join the competition, you won't be able to look at the full data of this one, of the main time series. But for this one, the holiday events, I think this is publicly available. Okay, so before we run this, I've run this notebook earlier. Okay, so I have 3 versions of NBEATSx here. I'll explain later. But let's now start with NBEATSxi. So this is the forecast generated by NBEATSx using interpretable configuration. Okay, so this is the prediction. All right, let's submit it. Okay, let's see. The score is like this, 15 and 14, all right? And this is the forecast generated by NBEATSx, the generic configuration. Okay, let's submit it and see how it performs. We can see that this error is generated by the NBEATSx-G. It's a lot higher, so it's a lot worse than NBEATSx interpretable configuration. Okay, and now let's see the last one, the last version. I denote it as A, NBEATSx A, and A is for all actually. I'll explain what I did with this particular model. Okay, so using the NBEATSx-A, we get 64 in the private score and 67 in the public score. The private score is the final one. So from these 3 models, we can see that NBEATSx with interpretable configuration is the best model because it has the lowest error. The metric is using SMAPE, by the way, so the lower the score, the better it is. However, this is still not the best model. So for this particular project, I use NBEATSx and I submitted 5 times. And the best model among these is this one, NBEATSx-A with polynomial degree of 1 and 1,000 iterations. And the total n-harmonic is 2, by the way. I remember this one. But the code that I will present to you in this coding section will cover these three. And well, I joined this competition in January 2022 and I could get even lower scores. I just used LGPM. Well, what did I use? Random forest, I think, but I could get 5.9. So yeah, this is kind of a failure project again, but I think I know why NBEATSx is not the right model for this dataset, and we're going to explore that as well in this coding section. Okay, we're going to apply NBEATSx with the neural forecast library. It's the official implementation. Okay, and then we need to import the libraries. Actually, this line here is not needed, but yeah, I'll show you later. You can choose to use this, to use time series dataset to train your model, but I'm not going to do that. Okay, now we have several datasets. The train dataset is here in train.csv, and then the test dataset is test.csv. The test set is basically just the timestamp and the unique IDs. Okay, and then the sample submission, this is for the template for submission, and then we will fill that out, fill the sample submission file, and yeah, so basically what I submitted earlier is the modified sample submission. Okay, and then the holiday events, the holiday datasets is here. Let's load them. So I load the train dataset as df, and then the test.csv is df test, and the exogenous variables is in holidays exogenous. Okay, now let's see the first few rows of df. Here it is. We can see that df is sorted by country and then store and then the product. So it doesn't look like a time series yet. We can see that the date is January 1st, January 1st, January 1st. So yeah, it doesn't look like a time series yet. We're going to get to that in a moment. But first, let's take a quick overview of the whole df. Yeah, we can see that we have 3 countries and 2 stores and 3 products. That's why we have 18 time series. And then I want us to look at this part. The earliest date of our time series is January 1st, 2015, and the latest is in December 31st, 2018. This is the time span for the train dataset, or for df. Now for the df test, it's like this. The earliest date is January 1st, 2019, and the latest is December 31st, 2019. Okay, so we have to predict the sales for 2019. Okay, now let's sort our data set. We sort it based on product and then store and then country. So this is our modified data frame. We can see that now it looks like a time series. So the first time series would be the time series for Kaggle hat in Kaggle Mart store in Finland. And yeah, this is the series. We can see the date is ordered correctly now. I'm going to keep the row ID. I will need that to make the submission file. Okay, let's plot this. Since we have 18 time series, I am going to lay out in facets or in grids. So the rows are for countries and the columns are for stores. Okay, so let's look at the first row. The top row here is for the products in Finland, and then the second is for Norway, and the third one is for products in Sweden. And then the plots on the left column are for sales history in Kaggle Mart, whereas the plots on the right column is for Kaggle store. I use different colors to differentiate the products. So the green lines are for hats, the purple lines for mugs, and the blue lines are for stickers. we can see that the seasonality pattern is so clear for each product, no matter where the store and the country is. So, for example, let's focus ourselves on the Kaggle hats plots, which is the green lines. They look so similar to sine functions, right? Even though they might have different intercepts or they might have different amplitudes. And then for the time plots for Kaggle mugs, they look like cosine function. And notice that the sales peaks, which happened around the end of the years, they get higher by the year. This pattern occurs in almost all products. Furthermore, the trend component in Kaggle hats and mugs is not as clear as in Kaggle stickers. Okay, perhaps we can see it better in the following plots. So I enlarge the plots for each product, but yeah, I kinda take it randomly. So only one plot for hats, one plot for mugs, and one for stickers, because all of them look the same anyway. The shape in general looks the same. Okay, so this is for Kaggle hats in Kaggle store in Norway. It seems pretty level. So we can see the seasonality pretty clearly, but for the trend component, it seems to level, or maybe just very weak trend. And now this is for mugs, Kaggle mug in Kaggle Mart in Sweden. We can see that the peak here is getting higher and higher. By the way, the index might look suspicious because we have 4 years of data, then it's not supposed to have 25,000 data, right? I think this is just the index, I mean the ID of the row. So let's verify that. So yeah, if we take just the values, then we can verify that it's like this. Okay, it looks the same, but the index is now different. Okay, and then the last one is this, stickers. Stickers in Kaggle Mart in Finland. And yeah, it doesn't have the seasonality except for the peaks at the end of the years or the beginning of the years. But yeah, it has a trend that is more clearly visible than in mugs or hats. Okay, so let's move on. This cell, I do a little pre-processing, which is removing the prefix Kaggle, so I don't need to mention Kaggle hats, but instead I can just say hats, mugs, stickers, and then Rama store and Mart store. So that was for DF and DF test. Now let's move on to the exogenous variables. Okay, so this is the holidays exogenous dataset. It has the local name and the English name and the country in which the holiday is celebrated. But actually what we need is the country and date, right? So I make a new column that actually I want it to be a binary variable, but this is how I do it. So I make a new column named holiday code, and I just give it 1 because it is a holiday, and then I merge it in the next cell. This will create some NA values, right? And then I fill the NA with 0. So this is the pre-processed DF now. I need to do this because NBEATSx take exogenous variables as numbers. So we need to pre-process our exogenous dataset into a numeric or a data that can be processed by the model. Alright, so that was DF. To prepare the exact data that we want to put into the model, we need a special data. So next I'm going to define the data. Okay, the data that I will use for the rest of the project. And it is a data frame with these columns. So DS is the date stamps, and basically I'm just taking the date column from DF and then the unique ID. we don't have the unique ID previously, because in df we have these columns: product, store, and country. And so to create the unique ID, we need to combine them. The holiday is for the exogenous variable and y is for the main time series. So I take the num sold column from df. After that, I split the data set. So I'm going to hold out the last year for the validation. Okay, so this is how the data, the data T is for train. This is how it looks like. So the unique ID is het mart Finland or het mart Norway, like that. So the first part is the product, and then the second is the store, and then the last one is the country. Okay, and then this is for the exogenous data frame. We need to do that for the requirement of the model as well. Okay, now let's do the modeling. I showed you earlier that we have 3 versions of it, right? So this is the first one. The first one is the interpretable configuration. Just like in the theory section, interpretable configuration uses trend, seasonality, and exogenous stacks in that order, okay? So the input time series will go through the trend stack, and then the difference between this input and the backcast of the trend stack will go to the seasonality stack and then exogenous stack. We can see that we have only one pink box in each purple boxes. So yeah, we have only one block in each stack. Okay, this is the default value and I just go with that. So yes, this is something that we can play around. Okay, and to instantiate the model, we use NBEATSx, and then we put in the horizon, and then the input size, which is the L, and then future exogenous list. We define the exogenous variable, and then the polynomial's degree, the total harmonics, and then the stack types. The stack types should be a list, and we just list out the stack that we want to use. And then the max steps defines the total iterations. The default loss functions that is used to train NBEATSx is actually MAE. But since the metric used in this competition is SMAPE, this is what we use for this loss. Okay, and then alias is for naming the model. If you wonder why I use n-harmonics equals 12, this value is actually abruptly taken, but here's what I thought. So in the traditional time series, traditional Fourier finite series, if the length of the time series is n, that means we have n divided by 2 harmonics. And we have a very long input sequence. Even if we want to say that our n or our length of the series is 365 because that's the total value that we need to complete a cycle. A cycle as in this one. We need a year to complete the cycle, right? If we need 365 values as our n, which means the total harmonics would be n divided by 2, and we might want to subtract 1 of it so that we can get an even number. That means we will get 182 as our total harmonics. I think the information that we can get from 180th harmonic and the information from the 100th harmonic might be negligible. So I just want to take the first few harmonics that perhaps can give us the most information. Okay, let's run this. So I stored this as NBEATSxi. And the second version is the generic configuration. Just like in the theory section, this configuration has 2 stacks, which is identity and exogenous. And just like in the interpretable configuration, we have only one block in each stack. And then for the third model, yeah, it's already written here, just for the sake of curiosity. So it's actually not stated anywhere in the papers, but I was just kind of curious. What if we take the trend and then seasonality and exogenous components out of the time series, and then the rest, or like the residue from those 3 stacks, is further decomposed by the identity stack? So that's my idea. And so because we have 4 stacks here, I have to modify the MLP units so that I can have 4 stacks, and I want to have 1 block in each stack as well. Alright, so this cell might be confusing. So NBEATSx, in neural forecast library, we have 2 ways of training our model. The first one is we list our models and state our frequency, which is daily, and put it in the neural forecast function and create the model. Okay, let's run this. And the second way is just use the fit method from the objects that we have instantiated. So if you look at the help, if you look at the help of these objects, their classes are different. So like NBEATSxi, for example, the class is NBEATSx. Okay, they have the fit method, but the dataset that can be put into the fit method here is the time series dataset. I tried that the other day, so that's why I needed the time series dataset in the imported libraries. Okay, so this is the class of the model, neural forecast. So it's a different class, and for the neural forecast class, their fitting method accepts pandas data frame. In fact, they don't accept time series dataset from Torch. But I'm going to fit the model using model, so using the fitting method from model, because this class allows me to fit several models in a data frame. Okay, so a little bit behind of the scene story. I said a few minutes ago that I tried using time series dataset and it didn't work out well because, actually I can fit the model, but I cannot decompose it. So in the theory section earlier, we saw that we can get the forecast at the stack level and then aggregate them to get a global forecast, right? And if we see the documentation here, we have the decompose method. So we can actually see the decomposition plot of the forecast. So that looks very interesting, right? But unfortunately, this cannot be done with NBEATSx. So yeah, that's why I just gave up and used the model, the model from the neural forecast class. Okay, we have fitted all the models. Now let's predict it on the validation dataset. Based on my understanding, this model is used to generate the age values ahead. Since our age or our horizon is 365, that's why we don't need to provide the train data anymore. Because using the stored dataset, we just need to ask the model to predict the next 365 values. And then future DF means that the values of these exogenous variables are already provided before the prediction happen. Okay, and so these are the values of our predictions. Looking pretty decent in my opinion. Okay, but let's look at the scores. Oh, by the way, these are the unique ID orders of the predictions. It's ordered just like in DF. Okay, so had Mart Finland, and then Norway, Sweden, and then had Rama Finland, and so on. Okay, so this cell is going to take the SMAPE from each series and each model. So this is to go over the models, and this loop is to go over the time series. Okay, and then I'm going to take the mean scores for each model. So I've put the average error in the title section. We can see that the error from all stacks used is the lowest. And then the interpretable and generic configuration give very similar error. But we can see from this plot that the error from the interpretable configuration is overall better than that from the generic configuration. Okay, in this visualization, I plot the ground truth values in dark purple and the forecast in light purple or perhaps pink. Okay, so this is the forecast from NBEATSx A. So using all the stacks that we learned. So the advantage of using all the stacks is, in my opinion, they can predict the peak at the very end quite well. But for some products, I think the model overestimates. Like in this one, for Het Mart Sweden, the forecast generally overestimates the ground truth. Okay, now let's look how NBEATSx I perform. So the interpretable configuration. Here it is. Here you might not be able to see the forecast lines very well, but they almost don't have the volatility, just very few. This model can only generate the overall trend in very broad sense. So that's why, for example, like in Rama, Norway, we can see the curve here, a little curve, but that's it. So they cannot predict the peak at the end of the series. Now let's look at the performance of the generic ones. Okay, for the generic ones, the forecast looks okay. Like we can see the volatility, and we can see that the volatility mimics of that from the ground truth, but they generally overestimate. Okay, now let's retrain the model. For this one, I'm going to retrain it using all the data in DF. Okay, so I'm not going to split the data anymore. Okay, so we're done with retraining and predicting it on the test set. What we just did now is that we use all the training data that spans from 2015 to 2018 to generate the forecast for 2019. So yeah, we can verify that here. The prediction, it starts from 2019 January 1st to 2019 December 31st. Now let's see the prediction that is generated from NBEATSx I. Okay, so this is it. For some products like mugs, for example here, these two rows, they can mimic the curve, but that's it. No volatility whatsoever. Okay, now let's look at the predictions from the generic configuration. Okay, so here it is. It looks better than that of the interpretable configuration, even though the forecast for stickers are quite suspicious for me. Like, it doesn't look really continuous with the rest of the series. But notice one thing. This also occurs in the previous plot as well, which is from the interpretable configuration. Yeah, so if you look at all time series, let's just say this one here, Gaggle Mart in Norway. I told you in the exploration section earlier that the sales for the end of the year gets higher and higher over the years. So actually we are expecting the forecast at the end of the year would be the highest among all the end of the years, right? But that's not the case. That's not the case in this model and the previous model. Okay, so now let's look at how NBEATSx performs. Okay, so these are the forecasts generated by NBEATSx. And yeah, the peak is not, well, it's at least as high as the peak of the first year, like in Het-Rama Finland, or Het-Rama Norway, or Het-Rama Sweden. But for hats in Kaggle-marts in 3 countries, that is not the case. And so do the forecasts for mugs in Kaggle-mart stores or in Rama stores and for the stickers. So I think this is the key to why NBEATSx cannot be the suitable model for this dataset, because these time series have multiplicative decomposition, meaning that we can decompose the time series into trend, then seasonality, or exogenous, residual, and then to combine those components into the time series that we have to multiply those components. That is multiplicative decomposition. In additive decomposition, though, we can just add the components. The fact that we cannot get the highest peaks in all forecasts shows that NBEATSx cannot perform multiplicative decomposition. And actually, that shouldn't be surprising, because that is the feature, not only in NBEATSx, but also NHITS and NBEATS. They aggregate the forecasts at the stack level by summing them up. So it's an additive decomposition, actually. So I think the lesson of this video, of this project, is that deep learning models are not always better. So we always need to look at the nature of the time series, and if that time series has an additive decomposition, then we have a huge chance of success by using NBEATS or NHITS or NBEATSx. But otherwise, we might need to look for other models. Alright, the rest of the cells are just for making the submission file, but we have done that earlier, so yeah, I don't need to run this anymore. This is the point of this video, why NBEATSx cannot be used. So if Kaggle stores are real and I really work as their consultant, I wouldn't recommend this model. I would try to look for other models. Okay, so that's it for today's video. I hope you enjoyed today's content. If you enjoyed this content, don't forget to hit the like button, and I'll see you next time. Bye bye.